We're going to look a little bit more at end behavior of functions. And what that means is another way of saying limits as x approaches positive infinity or negative infinity. So how will we formally write a definition of a limit as x approaches infinity? Well, we'd write it this way. For a real number L, which is going to be our limit value, and a function f, we say the limit as x goes to infinity of f of x equals L if and only if for every real number epsilon greater than 0, there exists a real number L, which is also greater than a real number n greater than 0, such that if x is greater than n, then f of x is between L minus epsilon and L plus epsilon. So we can see this graphically. Wrong one. Here we go. So here we've got a function f of x is 1 over x, and the limit as we go to infinity is 0. So this is approaching 0. We can see that informally. So the way this works out is we can slide this point right here to pick a particular m value. And let's say we're here, and let's say we start with a no, it's the epsilon we need to change here. Delta doesn't play into this. Okay. So if we say start with 5, we see that we could pick somewhere in here like this, and from that point on to the right, all of the y values are below that L plus epsilon and above that L minus epsilon. So now what if we pick a smaller epsilon, like say 1? Well, now where the m is right now is down here. Okay, then we see that some of the y values are above, so we need a bigger value for m. And so we go on out a bigger value of m here. The c doesn't even apply here, so let's just get rid of that. It's kind of in our way. Okay, so as we go out here further, we pick an m. Actually, we could pick it right there would work, whether it be the smallest m we could pick or something bigger m. From that point out, the y values are all below L plus epsilon and above L minus epsilon. And so the point is no matter how small we make this epsilon, say 0.1, okay, we need to zoom in a little bit probably to see it, but there's probably some place I can go out here. Looks like we've made, maybe, let's see here. Not quite there yet. Okay, we need to be over in here somewhere. Then if we go out, say out to here, now we see, as we zoom in a little closer, we see that from there on, the blue graph is between the two green lines, so the y values are between L minus epsilon and L plus epsilon. And of course, since this has a limit, because no matter how far out we go, that works out. And the same thing works for over here. If this is m, then minus m is over here. So the limit as you go to negative infinity says you can pick some m value. Say this is m value, which is negative. So I can just switch it over here. Here's an m value, which is a negative value. And from there out, the y's are less than the epsilon. Let's go back to a larger epsilon. Okay. And so there's some point out here beyond which, say actually right in there would do it, or even further out, so that all the y values are between here and here as you go further to the left. So that is that's the picture that we want to be looking at to help us explain what's going on. Okay. So I will, before I post the notes, I'll add a picture of that right in here. Now, when the limit of x approaches infinity is actually a constant number L, there's actually a few choices of what might happen, or a few possibilities of what might happen with the function. One of those things could be that from some point on, like here from about 7 on, the function actually is the line y equals L, and it actually hits that line and actually stays on it. So it actually is a horizontal line from some point on to the right. Another way, it could be like the one we looked at here. This is 1 over x, I think, here again. And we could have a horizontal asymptote approaching from above. So here, the graph, if we zoom in closer and closer, we can see that the graph of the function is always above y equals 0. 0 is the L value. But it gets closer and closer to that as we go further and further to the right. So it never actually touches it on the far right. Doesn't touch it at all, in fact, but in this particular case. But it gets closer and closer. That's a horizontal asymptote. Similarly, we have a horizontal asymptote on the left as well. Now, another way we could do it is the horizontal asymptote could be on the right, but it could be coming from below. Like this is probably a flipped over exponential or something. So it's coming up this way and approaching closer and closer to 5. So here, in the previous one, the y's are getting smaller and smaller and smaller, but get closer and closer to L. Here, the y's are getting larger and larger and larger, but getting closer and closer to L. That's also a horizontal asymptote. It's on the far right. It doesn't actually touch that line y equals L, but it's getting closer and closer to it as we go out. Now, there's at least one more possibility here. And this is an example of what we call damped oscillation. So this function is going up and down forever and ever, but it's going up and down less and less. So no matter where you pick a value of m out here and you go further to the right, it's going to go above and below the x-axis in this case, above and below the limit of 0. And it hits 0 from time to time, periodically, but the amount it's going up and down is less and less and less. So we can see that the limit actually is 0 in this case. So those are sort of the three or four possibilities that could happen there. As x goes to negative infinity, it's very similar. For every real number L, or we have a real number L that's a limit, and a function has that limit as x goes to negative infinity. That means that's if and only if for every epsilon greater than 0 there exists a real number n, which is a negative number, such that if x is less than that number, then L minus epsilon is less than f of x, which is in turn less than L plus epsilon. So same way. So in either case, we're approaching a horizontal line in some way or the other. All the different ways you could approach on the right. If you have a limit on the right, you have the same kinds of graph shapes as possibilities if you have a limit on the left. It's sort of the mirror image of it. So in either case, you're approaching a horizontal line. It's just a matter of whether of how you're doing it. Okay. Examining limits as x approaches infinity or negative infinity is also known as determining the end behavior of a function. And notice that this terminology is really a misnomer because the function doesn't really have an end to it. Typically, when you have limits as you go to infinity or minus infinity, the function goes out forever to the right or forever to the left. And so it doesn't really have an end to it. But it's still called end behavior for what happens way out on the far right and the far left. In the next video, we'll talk a little bit about limit laws and how we might derive and prove some of them.